Alrighty, so here I'm going to be going over the progress check FRQs. I started going over them, but then the initial video kind of messed up. So anyways, I already started the very first one. So let's review part A. So part A, we have these two carts here, cart 2 and cart 1. I know I already have some writing on it, but basically what's happening is there's an applied force on these carts, and that function for that force as the function of time is mg times e to the negative t over tau, where tau is a positive constant, and it's the force exerted on each cart in the positive x direction. So basically, we have to sketch a graph of the net force acting on cart 1 as a function of time, and the time t max indicated on the time axis, where cart 1 has a maximum velocity in the positive x direction. Okay, so here, basically what I did was I labeled some critical values that the function has to have, right? So these are the critical values here, and I'm going to explain why those values are what they are. So if you look at what's going on here, I can kind of like draw it out again. So we're just working on cart 1. So cart 1, let's evaluate it at a time t equals 0. So when t equals 0, right, the force when t equals 0, this applied force, is going to be equal to mg, right? Because e raised to the negative 0 over tau, right? So just basically it's just e to the 0. That's going to be equal to 1, okay? So that is going to be the applied force. But you can't forget that there is going to be a component of gravity that is pulling the cart in the opposite direction. So I have this mg sine theta over here, and I believe I wrote it up. Yeah. So over here, we're looking at the net force on cart 1, and I have this function, this mg times e to the negative tau over t, or t over tau, minus mg sine theta. And at t equals 0, this is my expression for the net force, okay? So mg minus mg sine theta. So critically, you have to put the very first point, it has to be less than mg, right? Because it's mg minus mg sine theta. So some value between 0 and mg. And I would actually have it mostly make sense, right? So if you could put the dot here, or you could have put the dot like over here, right, where it's just above 0. But I mean, if you look at the system and you think about what's going on, right, this angle, this theta over here is not particularly large. So mg sine theta is not going to be particularly large either. So even though you still are going to get credit, right, you can put the point anywhere, like have it actually make sense. It's going to definitely be closer to mg, then it's going to be closer to 0, because mg sine theta should be fairly small, just based on the image that they show us, all right? So that's one critical point. And then the other critical point here, t max, this is also very important. You have to understand that that's when the acceleration is 0. So it specifically says in the problem that at time t max, that's when the cart 1 has a maximum velocity. So if you think about what's going on here, the applied force is going to be greater than mg sine theta at t equals 0. All right, so this cart is going to accelerate up the inclined plane. Its velocity is going to be increasing. So it starts off with some initial velocity. Actually, I can redraw that. So it's going to have some initial velocity, and that initial velocity is going to be increasing with time. But it's going to reach this point here where where it reaches maximum velocity. So at maximum velocity, it's important to note that the acceleration is going to be 0, right? When you reach maximum velocity here, the slope of the tangent line is going to be 0. So acceleration is 0 at Vmax, which means that the net force is also going to be equal to 0 at that critical time. So that's this data point over here. At Tmax, we know that the net force is 0. And then the minimum value that it achieves, some time, much greater than 0, it's basically going to be just negative mg sine theta. And the idea with this is that at some time much greater than 0, well, then t is going to be much larger than tau. So we can think of as t approaches infinity, basically you have e to the negative infinity, and e to the negative infinity is 0, right? So as t gets much larger than tau, then that applied force is going to be approaching 0. And then the only force that's going to be acting on cart 1 is that component of gravity that's pulling it down the inclined plane. Okay, so that's this critical point here. And notice that I make it closer to 0 than I do negative mg, just because that sine theta term is going to be fairly small. But you could put it anywhere in between 0 and negative mg. Now, in terms of the shape of the curve, all right, so that's also important to get full credit for this problem. You need to know that e to the negative x, like a decaying exponential, has this rough shape, okay? And it's going to be approaching, if I just have e to the negative x, right, it's going to be approaching 0, right, as x becomes larger. And then it's shifted down because I have that minus mg sine theta over there. So these are my 3 critical points, and then I draw the curve that looks like a decaying exponential. And that's part 1 for part A. And then the second part, you have to derive an expression. So I kind of started it over here. All right, so let me kind of walk through it one step at a time. Here, the idea is it's asking about the momentum of the system as a function of time, right? So we have to derive an expression for the momentum of the system for times greater than 0, where t is greater than 0. We have to express our answer in terms of m, t, v naught, theta, and tau, and any other physical constants as appropriate. So notice that it's asking about the momentum of the whole system, right? Not just of cart 1. So the first problem was asking about cart 1. Now we're looking at the entire system. And that's this expression over here, right? So the net force acting on the system, okay, it's actually 2 times f of t, right? Because I'm looking at the whole system here. I have 2m and m for carts 2 and cart 1 respectively. And there's an applied force on cart 1 and there's an applied force on cart 2, where that force is equal to mg times e to the negative t over tau. So I have 2 times that applied force. Then I have mg sine theta going against the system, or 2 mg sine theta for cart 2 and mg sine theta for cart 1. So this expression that I underlined in green, that's the net force acting on the system. And then the way we're going to derive an expression for the momentum of the system, well, we know that it's going to equal the initial momentum of the system plus the change of momentum that's acting on the system, right? So that change of momentum is going to be changing, right, as time goes on, because the force is changing with time, or the net force on the system is changing with time. And so what we're going to use is the impulse momentum theorem, right? So we know that the change of momentum is equal to the impulse, which is equal to, actually write that down. So the change of momentum is equal to the impulse, which is equal to the integral of f dt. All right. So that's what I do here. I have my net force on my system, right? So 2 times f of t, right? So basically it's 2 times f of t minus 3 mg sine theta. And that's this part that I put over here, right? So I write down the expression, and then I am going to evaluate the integral, and I end up with this expression over here. All right, so now let me talk about integrating this exponential, this e to the negative t over tau. So some things that we need to note. All right, so as a quick little review, I wrote these up on the board, but again, this is kind of one of our first times looking at the integrals and derivatives for e to the x. So the integral of e to the x is just e to the x, as a reminder. And a derivative of e to the x is, well, e to the x. That's what's cool about e to the x. It's kind of how e to the x is defined, actually. But now if there's a coefficient in the exponent, well, you need to know that if I integrate e to the ct, I get 1 over c times e to the t. And then a derivative of e to the ct is c times e to the ct. Okay? So then if I have this, this integral of e to the negative t over tau, I can write that as e to the negative 1 over tau times t. And then when I'm integrating, right, I'm going to do 1 over c times e to the t. So it's 1 over negative 1 over tau times e to the negative 1 over tau times t, and I get this expression over here. So I know it's a bit much, but it's important that you evaluate your integrals and derivatives properly. So this is the expression that I get here, right? So I know that the integral, I'm just looking at the exponential part because that's the part that can be confusing. All right, the rest of it's pretty simple. So for the exponential part, e to the negative t over tau, the integral of that is negative tau times e to the negative t over tau. And I write that over here, right? So notice I had positive 2mg times e to the negative t over tau, and then this negative tau comes out in front. So then I have this expression here, negative 2mg tau times e to the negative t over tau. And then the negative 3mg sine theta, well, that's just a constant, right? That force doesn't change. So, when you integrate that with respect to time, like if you integrate a constant, well, it's just going to be c times t, right? So I just put a t there. So that's the integrated expression. And then we have to put in our bounds of integration. So from t equals 0 to some later time, t equals t. And then that's what I do over here. So I plug in t first, right? So when you're evaluating the bounds for integration, you start with the upper bound, and then you subtract from it the expression when you put in the lower bound. So from the upper bound, I have t. So I have this expression over here, right? Negative 2mg times tau over negative t over tau minus 3mg sine theta times t. And then I'm going to plug in t equals 0, right? So this part over here, the mg sine theta, well, times 0, that whole thing turns to 0. But e to the negative 0, as I mentioned earlier, that's equal to 1, all right? So now I have minus negative 2 mg tau times 1. And then this is my expression over here, right? So now I'm at this expression over here. So notice it's minus negative 2 mg tau, so that turns into plus mg tau. And to simplify this overall expression, I'm going to factor out a 2mg. So I have 2mg times tau, or actually there's a tau in both. So I'm going to factor out mg tau. So I have mg tau here times 1 minus e to the negative t over tau. Okay, minus 3 mg sine theta times t. Now that's equal to my change in momentum of the system, right? So this is the impulse acting on the system, but we're looking for the momentum of the system, like the entire equation, as a function of time. So this system has some initial momentum, right? Because these carts start with some initial velocity, right? This is just my impulse acting on the system. So my final expression, so P of the system, right? Cart 2 has a mass 2m v naught, and cart 1 has a mass m v naught. So P naught is basically 3m v naught. So my momentum of the system as a function of time is 3m v naught times, I'm sorry, not times, what am I saying? Plus this impulse acting on the system. So plus 2 mg tau times 1 minus e to negative t over tau minus 3 mg sine theta times t. All right. And one thing you can do when you have your final expression is you can kind of evaluate it and see if it makes sense, right? So we know that at time t equals 0, we should just have 3m v naught. We just have the initial momentum of the system. And that momentum of the system is going to increase a little bit at the beginning because the applied force is going to be larger than the component of gravity that's going down the plane. And then that momentum of the system will start to decrease. It's kind of like with the graph for cart 1, right? There's going to be a positive net force at the beginning, and then that net force is going to become negative as time goes on because the applied force approaches 0. So yeah, if I set t equals 0 for this expression, right, I have 1 minus e to the negative t over tau. Well, e to the negative 0 is just 1. 1 minus 1 is 0. And then this negative 3 mg sine theta times t, well, at t equals 0, that's 0, also 0. So I just have 3 m v naught It's always good practice to kind of like when you write your final expression, especially one that's got so many terms like this one, that you double check and make sure you got it right. So that's quite a bit of math, but that's what we need to know how to do for some of these problems. All right, so for the rest of this, I would say it's smooth sailing. Yeah, notice, yeah, part A, oh my, that's 7 points if you look at the scoring guidelines. So that one's a bit of a doozy. But now let's look at part B. Now we have a new situation. So the carts are placed back in their initial positions as shown in figure 3. This time there's no force F of t. And cart 1 is released from rest at time t equals 0. Cart 2 has velocity v naught in the positive x direction. And then they're going to stick together. So it's going to be a perfectly inelastic collision. And we have to derive an expression for the velocity of the two-cart system immediately after they collide. And then we're going to express our answer with the same kind of physical constants. So for part B, again, we're going to use conservation of momentum. All right. So we know that the initial momentum is just going to equal 2m times v naught, right? Because cart 2 has a mass of 2m. And then they're going to stick together, right? Because a perfectly inelastic collision. But they also have an impulse acting on them, right? So that impulse actually comes from the weight of the carts, right? So now there's no applied force acting on the system. I'm sorry, there's no applied force, but there's still the force of gravity, right? So there's still a component of the force of gravity that is going to be decreasing the momentum of the system as time goes on, right? So don't forget about that. So this component here, we got 2mg sine theta, and then this component here is mg sine theta. So don't forget about that. So the final momentum, we know that these carts are going to stick together, and we're just writing an expression for the velocity of the two-cart system immediately after they collide. So we know that the final momentum, they're going to be stuck together, right? So the final momentum of the system is equal to 3m times vf, all right? But this final momentum is not going to equal the initial momentum. And the reason for that is because there's an impulse, right? So there's going to be a change in momentum that's caused by the impulse, right, acting on the system. Now, fortunately, it's just a constant force, right? So if I look at the entire system, right, the external forces acting on the system is going to be this 2mg sine theta and mg sine theta, right? So basically, this is 3mg sine theta times delta t. All right, I guess I should put negative 3mg sine theta. So the final momentum is going to be smaller than the initial momentum because this impulse is going to be decreasing the momentum of the system. It's going in opposite direction. So when I write out my expression for the momentum of the system immediately after they collide, right? So I'm going to put PF is equal to the initial momentum of the system, which is 2m v naught, minus this impulse that is acting on the system. So actually, hold on, my bad. It's asking for an expression for the velocity. All right, so here, and it's not for the momentum, it's for the velocity. So the final momentum is 3m vf, right? Because the carts are going to stick together. So they're going to act as a combined mass. And that's equal to initial momentum minus the impulse caused by the component of gravity. So that's 3mg sine theta times delta t. And then basically we're going to divide everything by 3m. So the momentum after the collision is going to equal 2 over 3 v naught minus g sine theta times delta t. And that's our final answer. All right, so that was not too bad. All right, so now let's look at FRQ number 2. Let's see here. Here it is. Okay, so for FRQ number 2, let's do our markup. All right, so we have these two. We have a child and an adult, and they're ice skaters, and they start with some initial momentum where they're moving to the right with some velocity v naught, and then they're going to push off of each other. All right, so for part A, we have to draw a free body diagram. Now, for this one, again, the free body diagrams, these are supposed to be the easy points, but just be careful. All right, so don't rush through these. Make sure you label your forces properly, and then for this one, the relative sizes of the forces matter. All right, so note the relative lengths of the arrow should reflect the relative magnitude of the forces. All right, so don't mess this up. Actually, it looks like I crossed it out. But yeah, no. So make sure that the lengths of the arrows actually make sense. So here, this is going to be for the child skater. And here we have the adult skater. And I think it even specifies. So the adult is twice as massive as the child. So right off the bat, we know that there's going to be gravity, right? So here, we're going to put the force of gravity acting on the child, okay? And this here, this is going to be the force of gravity acting on the adult. All right, so notice I drew that 2 times larger because it's twice the mass. It should have twice the force of gravity. And then I have to do the same thing with the normal force. So this is normal force acting on the child. And this is normal force. Oh, whoops. See, this is what you gotta be careful. All right, that's going to be... There we go. All right, so this normal force obviously has to equal the force of gravity because it's not accelerating up or down. And one other thing I want to mention, so when you're working through these FRQs, after you submit, I think you're able to get access to the scoring guidelines. So I put the option where you can check your own answers. So if you want to look at the scoring guidelines, you should get access to them after you submit the FRQs. But anyways, so notice how I'm labeling my forces, right? So I'm drawing the arrows. They're consistent in terms of the size. I'm labeling all my forces with a capital F, and I have these subscripts here. And actually, you do have to have different subscripts for the different skaters, right? Because the idea, if I just put Fn and Fg, right? Well, you know, when you're writing out equations and you're using Newton's second law and using the free body diagrams, you have to have different labels for the different forces, right? So normal force on the adult is different from the normal force on the child, all right? So that's why there's these additional subscripts here. And then finally, when you write the force of the, you know, from the collision, they're going to push off each other. Here, I'm going to put F of A on C. So the adult pushed the child to the left. And because of Newton's third law, the child is going to push on the adult going to the right. Right. So these are equal and opposite forces. So make sure you draw that on your free body diagram. And yeah, that's pretty much it. That's part A. Those should be the easy points. All right, so now we have to derive a final velocity for the adult skater in terms of m, v naught, and physical constants. Well, let's see. What does it say here? Okay. The two skaters have initial velocity, because we need to know one other piece of information. All right, after the skaters push off, this child moves the final speed of v naught over 3 in the negative x direction. All right, so now we can derive our expression. I'll derive it over here. Well, the initial momentum of the system is just equal to, right? So we have mv naught over here for the child, and then we have 2mv naught for the adult, right? And then the final momentum of the child is going to be m v naught over 3 traveling to the left, and then the momentum for the adult is unknown, right? So we have 2m times vf for the adult. We don't know what vf is. So when we do conservation of momentum, right, we know the initial momentum is 3m times v naught, and that has to equal the final momentum. Now keep in mind, don't don't mess this up. The final momentum for the child is going to be negative, right? Because it's going in the opposite direction. All right, so be careful when you're doing conservation momentum. The direction of the vectors are important. So this is going to be negative mv naught over 3. That's the final momentum of the child. And then we have the final momentum of the adult skater. All right, so here, let's actually figure out what the final momentum is going to be. So I have m's in all these terms. So I'm going to get rid of the m's. I'm going to kind of rewrite this as 2 vf minus v naught over 3 is equal to 3 v naught. So I'm going to move these v naughts to the other side. And I get 2 vf equals, let's see, so this is like 9 over 3 v naught. So I'm going to have common denominators. I move that over, it's going to be 10 over 3 v naught. And I'm going to divide everything by 2. So Vf is equal to 10 over 6, which is 5 over 3 v naught. All right, so that's going to be the velocity of the adult skater. So Vf is equal to 5 over 3 v naught. And now let's see here. So it's part 2. Part C, we have to label the graphs when they push on each other and it's negligible compared to the scale shown on the horizontal axis. All right, so this is the position as a function of time before they push off and then after they push off, and we have to draw the position of each skater. So for the adult, we label it A. For the child, we label it C. And then we have to do it for the center of mass of the system, okay? And we're going to label that as S. All right, so now with this one, you want to be a little careful. Basically, what you need to understand is that this is a position time graph, right? So we have information about the velocity, and we know that the slope of a position time graph is velocity, right? So if I look at this initial slope, right? So before they push off, we start measuring t. T equals 0 is the moment that they push off each other. So notice that my slope, it goes up 3 units over this unit of t1, okay? And we know that the initial velocity of the system was mv naught, okay? So now we're looking at the velocities of each of the skaters, and then for the center of mass. So the velocity of the adult after the collision, we just figured that out to be 5 over 3 v naught. We know the initial velocity was, well, v naught. The velocity of the child was negative v naught over 3, right? So negative a third v naught. And then the velocity of the system is, well, going to be v naught. So actually, it's kind of important that they put the initial velocity, the slope of this graph, as 3 vertical units. It goes up 3 units over this time period, because the final velocity of the child is, well, negative v naught over 3. So I know that the child is going to be at this position after this time period. All right, and notice that the slope of this line is negative a third of the slope of the initial velocity of the system. All right, so anyways, this is the position of the child with respect to time, right? So they asked us to label that as C. And then for the system, it's going to maintain the same slope, right? Because basically the way you think of the entire system is you treat it as one large object, basically. So there's no external forces on the system, right? The child and the adult, they push off each other. So that's an internal force from Newton's third law. So we know that the momentum for the system is going to remain constant, which means that the velocity remains constant, which means that the slope of that line is going to be constant because the slope of a position time graph is velocity. So I'm going to label that S. And then for the adult, he's going to have a velocity of 5 over 3 v naught. So now I'm going to go up 5 units, and this is for the adult. So that represents the adult. So it's an interesting way to ask about basically what the final velocities are for the child and the adult. But don't be intimidated. Just go. I mean, obviously, we all know this fact, and just kind of reason how you're going to represent these velocities on this graph. And then D, indicate whether the final speed of the child skater is less than, greater than, or equal to the final speed v naught over 3. Okay, so now they're skating together with the same initial velocity, but this time they push off each other for the same brief time interval with a force half the magnitude as before. All right, and then we're going to look at the speed of the child after the collision. All right, well, if it's half the force, okay, here we have some force equal to, right, so we know that our change momentum is equal to the impulse, which is force times time. And then the time interval is going to be the same, but it's going to be half the force. So it's going to be half the change momentum, right? So now the new change momentum for, the second scenario is equal to half the change momentum for the first scenario. So let's look at what the change momentum on the child was in the first scenario. So the child has an initial momentum of mv naught, and it has a final momentum of mv naught over 3 going the opposite direction. So the change momentum of the child initially for like the first situation is negative 4 over 3 mv naught. Okay, and then in the new situation where it's half the force, it's going to have half the change in momentum. So it's negative 2 over 3 mv naught. So what's interesting for this one is that the speeds are actually the same, right? So the final speed of the child in the first situation was negative 3, right? So here I'm going to draw the little child. So in the first situation, after the collision, he's moving v naught over 3 to the left, right? In the second scenario, okay, his change in momentum is going to be negative 2 m v naught over 3, right? So if he starts off with mv naught minus 2 m v naught over 3, his final momentum is going to be mv naught over 3, but it's going to be positive, all right? So he's going to be moving to the right with a velocity of v naught over 3. So it's asking about the speed, right? So his final speed is actually going to be the same, right? So justify your answer, and that's basically the justification, right? So you reason that the change momentum for the child is half as much, but because of what his velocity is, right? So his velocity was going to be v naught over 3 to the left for the original situation, and then for the new situation where it's half the impulse, his velocity is going to be v naught over 3 going to the right. Okay, so that's why that's the justification for that one. So now let's look at number 3. For this one, this is one of the lab questions. So in the interest of time, I'm just going to pull up the scoring guideline. And I want to mention something that's actually important about this problem. So here we have a group of students. We have cart 1 and cart 2 of unknown mass, and a spring is inserted into cart 2, compress, use to launch both carts in the physics experiment. And they have a collection of blocks of known masses, which can be added to cart 1, and the cart moves with negligible friction in the wheels and axles. And then we have to experimentally determine the mass of cart 2, but the only measuring device is a meter stick, so they can't measure the mass directly, and they have a straight horizontal track with a wall at each end, and they can place the carts together and release them, and they can detect whether or not cart 1 or cart 2 hits the wall first, or whether or not the carts hit their walls at the same time. And that's really what you need to set up this experiment. Well, first of all, this is also kind of a silly situation because I mean, what, they only have meter sticks, they don't have scales, they don't have stopwatches. This is but they have fancy carts. But anyways, that's not the point. The point of this experiment is to see if you're able to design an experiment with limited resources. So this fact here is what you're going to use to construct your experiment. So the fact that the carts, you can hear if the carts hit the wall at the same time. All right. And so the basic idea with this is we know that we can compare the ratio of the velocities, right? So if we could measure the velocities of the cart using a motion sensor, that would be a lot easier because we know that they start off with 0 momenta and then their final momenta has to be 0. In other words, these carts are going to have equal and opposite momenta, right? So cart 1 is going to be going to the left with a momentum mass of 1 times v1f, and then cart 2 is going to be moving with a momentum mass 2 v2f. So cart 1 has a known mass, and they have other known masses that they can add to cart 1. So that's basically their independent variable. And then their dependent variable is going to be basically they're trying to figure out what the mass of cart 2 is. Now, if you had motion sensors, you can just look at the velocity. But if you're clever, you can set up the meter stick in such a way where you're actually going to be, instead of measuring the ratio of the velocities, right? So, you have to think, like, how would you do this experiment, right, with just a meter stick? Well, think about an easier way to do it where you actually have a motion sensor, and then that kind of gives you a clue as to how to do it with just a meter stick. So I know that the ratio of the masses, right? So let's say I want to solve for M2. Well, M2 is just going to be M1 V1F over V2F, right? So I can look at this ratio in order to experimentally determine M2. But we can't measure the velocities. We only have a meter stick. We don't have a stopwatch. We don't have a motion sensor. We only got a meter stick. So this fact here, when the carts hit the wall at the same time, that's what you're going to use in order to figure this out. And basically, for the interest of, because this one, it has a graph, I'm not going to be drawing a graph. I'm keeping the video short. But we practiced this before, and I'll highlight the important details. So here, basically, you're going to, did I skip it? All right, so I like this first response because they just keep it simple. They write a list of the things you have to do. You push the carts and release them, and basically they're going to, initially, if you put it in the middle and they have different masses, they're going to hit the walls at different times, right? So say that cart 2 hits the wall first, well, then you can move it more towards the direction of cart 1's wall. But basically, you're going to keep finagling the carts, keep moving them around until they hit the wall at the same time. All right, so as soon as they hit the wall at the same time, that's when you can use the meter stick, and instead of comparing the ratio of the velocities, you can compare the ratios of the distances, right? And this comes up in the later parts of the problem, but I want us to appreciate that fact, right? So we have M1 V1F. We know that has to equal M2 V2F. But if I write V1F and V2F in terms of the distances, right? So mx1 over t1 equals m2 x2 over t2. And when they hit the wall at the same time, right? So when they hit the wall simultaneously, t1 equals t2. And then basically I'm comparing the ratio of the distances. All right. So, it shows you how, even with limited resources, if you're clever, you can still do some interesting experiments. So here, this is the basic idea, right? So as soon as they hit the wall simultaneously, you can use the meter stick to measure the distance from each wall to the nearest part. And then later on in the experiment, you have to explain how you're going to figure out mass 2 from the data that you're gathering. And this is also something that's very important, all right? So you'll lose a point if you don't mention this. So the fact that you do repeated measurements, all right? You don't just measure it once, okay? So you're going to repeat these steps. You're going to do it multiple times for each measurement. So your independent variable is the masses on blocks of cart 3 different masses of blocks added to cart 2. Wait, isn't cart 2 the one they're figuring out? Cart 1. Oh, wait, what? Cart 2. Yeah, cart 2 is an unknown mass. The students have collection of blocks of different known masses, which can be added to cart 1. All right, well, that's a typo. Because you're going to be adding masses to cart move, yeah. To experimentally determine the mass of cart 2. Okay. No, we're cart 1. All right, whatever. So anyways. But what I'm trying to get at is that you're able to do multiple experiments, right? So when you just have cart 1 and cart 2, and you measure the relative distances when they hit the wall simultaneously, you're going to want to repeat that at least 3 times, and then take the average, right? So it's very important for science experiments that you take multiple measurements for the same value of the independent variable in order to decrease the variance of your experiment. So if you don't mention that, you'll lose a point. So yeah, they even talk about in the scoring guidelines. Describing valid method. Wait, hold on, I skipped it. Repeating the experiment with multiple trials using blocks of different masses added to cart 1. Actually, I don't, so why did they do this? This kid said cart 2. All right. Well, anyways, whatever. That's a typo. So now for part B, let's see here. So now we have a different experiment. Wait. Oh, never mind. I skipped it. All right. So data collected from part A. Describe how the students can create a linear graph and how that graph could be analyzed to determine the mass of cart 2. Well, it's what I was talking about earlier, right? You can set up the ratio of the distances instead of the velocities. And that's what they do over here, right? So actually, I'll show the linearization, right? So I have this ratio here. They use D instead of X, same difference. So D2 over D1 equals M1 over M2, right? So just like how we set up over here. And then your independent variable. So you're adding masses to cart 1, and then you're trying to figure out what the mass of cart 2 is. So what I'm going to want to graph is the ratio of cart 2, of the distance of cart 2 to the wall versus cart 1 to the wall when they hit the wall simultaneously. And you're changing M1. You're adding mass to M1. That's your dependent. That's your independent variable. Your dependent is the ratio of the distances. So here I'm going to have 1 over M2. That's what we're trying to determine, M2. And then M1 is my dependent variable. And then this little trick here to kind of figure out, what you're going to graph and how you're going to use the slope. So on the vertical, I'm going to put the ratio D2 over D1. On the horizontal, I'm going to put mass 1. And then the slope, I know that the slope is going to equal 1 over mass 2. So whatever slope I get from my graph, I take the reciprocal of that slope, and that's how I get mass 2. Right? Yeah, anyways, that's pretty much it. Yeah, so the best fit line will be the reciprocal 1 over M2, mass 2. All right. Now let's look at part B. All right, so part B, now what they're doing is they have a different cart 3, and they have a inelastic collision, but not a perfectly inelastic collision. All right, so the carts are going to collide with each other, and they have new velocities, and then basically he wants to determine the ratio, right? So what percentage of the kinetic energy of the system remains, right? So like how much kinetic energy does the system still have? So that's this ratio beta, kf over ki, right? So the final kinetic energy over initial kinetic energy. So then it says here what quantities could be graphed to yield a straight line that could be used to calculate an experimental value for beta. So when you're figuring out the kinetic energy, we know that the kinetic energy of the system before the collision, I'm going to have 1/2. Oh, wait, let me use this pen so it's a little bit finer. All right, so you have 1/2 m1 v1 naught squared. That's the initial kinetic energy, k naught. And then the final kinetic energy is 1/2 m1 v1f squared plus 1/2 m2 v2f squared. And then the ratio of beta is going to be this divided by this, so kf over k naught. And then you have to set up your variables in such a way that you can experimentally determine beta. So actually, I'll write that out because I think it's important to have practice with this whenever you have to do linearization. So I have KEF, right? So 1/2 m1 v1 naught squared plus 1/2 m2 v2 naught squared. Oh wait, why am I putting naught? My bad. F. This is the final. So v1f squared, right? So it's v1f, v2, right? v3f. Oh my goodness. V3, this is cart 3. All right, so ignore all the 2s I said. It's cart 3. All right, cart 3. Yeah, so M3 V3F. Okay. And I'm going to divide all that by the initial kinetic energy of the system, 1/2 M1 V1 naught squared. All right. So that's a bit much. We can simplify this a bit. So the masses are the same, right? Because that's would be a lot more annoying. Does it say that? Yeah, it has to say that. Identical cart. Okay, they have the same masses. All right, so I can basically factor out a 1/2 m, right? So if m1 equals m3, basically I'm just going to rewrite it as just m. So I can factor out this 1/2 m here and then move it to the other side. So I'm going to divide all of this, both sides of the equation, by... No, actually, hold on, because the 1/2 m, that kind of just factors out. Yeah. So I have 1/2 m in these terms, and then I have 1/2 m over here. So basically, beta is equal to v1f squared plus v3f squared all over v1 naught squared. All right. And we're basically going to want beta to be our slope. So what we're going to graph, the v1f and v3f, these depend on what v1 naught is, right? So the initial velocity of cart 1, that's our independent variable. So we're going to change that, and we're going to see what the final velocities are. So the way we're going to write this is v1f squared plus v3f squared equals beta times v1 naught squared. And then doing the same trick, all right, on the vertical, I'm going to want to put the v1f squared and plus v3f squared. On the horizontal, I'm going to want to put v1 naught squared, and then my slope's going to be beta. All right, so the ratio of the kinetic energies. So that's what we put there for part C, right? So on the horizontal axis, it's v1 naught squared, because they're independent, and then v1f squared plus v3f squared is going to be our vertical. And now for this one, all right, you have all the data. You have to crunch the numbers. I'm not going to do that. I'm just going to show you the scoring guidelines. But there's one thing that's very important about the scoring guidelines. All right, so I want to mention that. And it's in the interest of time. All right, I'm not going to be doing these calculations. So something that's very, very important, okay? When you are using points on the graph to determine what the slope is, you have to pick points on the best fit line. So you draw a best fit line that fits through all the data, and then you have to pick 2 points on the line specifically in order to get the slope, right? So here looking at... Now what's interesting is that you can set up your... actually, I don't like this. I feel, for like these ones here, it's a good habit to make your independent variable on the horizontal, because that's basically how you're doing the experiment, right? So you're changing one variable and you're measuring, how something else depends on the variable that you changed, right? Because that has to do with the the causation and correlation of the experiment. You don't want to get that backwards. But okay, if you do it the other way around, at least they don't punish you for that. All right. So here, yeah, so this is the term that they have for beta. And they're going to experimentally determine beta. The slope of the line is going to be beta. And then they pick 2 points on the graph, and then they determine what beta is. So, and yeah, what's interesting is that based on how you set it up, this probably has to do with just how it's rounded, right? If you're doing the square roots versus looking at the sum of the squares. But either way, it's going to end up being about 0.6, and that's how you set up this experiment. All right, so almost done. Last one. Let's look at the very last FRQ. Where is it? It's over here. Okay, so here we have two masses. They collide, and there's a region where there's no friction, and then a region where there is friction. And for part one, we have to determine the travel distances, D1 and D2, and indicate how D1 and D2 compare to each other. So in trial 1, the block has mass ma, and then in trial 2, the block that's incoming has mass 2ma, but then it says that it has an initial velocity of 1/2 v naught. Oh wait, whoops, I didn't do markup. Wait, how do I, yeah. Okay. All right, so it's going to have velocity 1/2 v naught, and we have to determine d1 and d2. So you might be inclined to say that they're going to be equal because they have equal momenta, but you have to really think about what's going on. Okay, so basically the idea here is, yes, they do have the same momenta. The system is going to have the same momentum in both trials, right? So ma is moving to the right with a momentum ma times v naught, and then this system, it's moving to the right with 2m times v naught over 2. So it has the same momentum. But the thing is, the velocity is going to be different, right? So ma is going to collide with mb, okay? And the final momentum of the system is going to be ma plus mb times vf. The final momentum of this system is going to be 2ma times or plus mb times vf. So they have the same initial momentum, but for this system, for trial 2, the total mass is greater. So then vf is going to be smaller for trial 2, right? So vf here, I have ma v naught divided by 2ma plus mb, but the final velocity over here, or vf1 I should say, is going to be ma v naught over ma plus mb. Okay, so this system in trial 1 is going to be traveling more slowly than in trial 2. And then if you analyze the forces on the system, right, because we're dealing with friction, so I'm just going to treat it as one big block. Technically it's two blocks, but these blocks are moving together. I know that there's going to be a normal force, and there's going to be the weight of the system, and there's going to be this friction force that's going against the system. And just to go through this, we've done this plenty of times. We know the Fun equation, right? Force of friction. This is kinetic friction, so it's just mu times normal force. And I know that the normal force is going to equal mg. And again, we're just looking at the whole system, which then I know the force of friction is equal to ma, right? That's the only force that's acting, that's actually accelerating the system, acting in the direction of acceleration. So ma is equal to mu times mg. I keep wanting to put sine theta. I'm so used to inclined planes. But yeah, in this case, just mu times mg. And then the m's cancel out. So I know the acceleration of the system is mu g to the left, right? These systems are moving to the right. Friction opposes the direction of motion. So they're going to have the same acceleration. To reiterate, trial 1, the velocity is going to be larger than in trial 2. Okay, they have the same initial momenta, but because the mass of trial 1 is smaller, the total mass, it has a larger velocity. and then both systems have the same acceleration. So that's basically the reasoning, right? So if they have the same deceleration, okay, and trial 2 has a lower velocity, well, trial 2 is not going to go as far, right? So D2 is going to have to be less than D1. D1's going faster, right? So trial 1, the final velocity after they collide and stick together is going to be larger. Therefore, it's going to go further for trial 1 versus trial 2. D1 is greater than D2. That's the answer to that one. Justify the claim. That's basically what I just said, right? So like they both have the same acceleration. The velocity for trial 1 is going to be larger because of conservation of momentum, and that the mass after the collision is going to be smaller. So that's why the velocity has to be larger for trial 1. Therefore, D1 is greater than D2. And that's basically it. Okay, there's a mild interruption. So I'm recording a second clip, but we're almost finished. We just have to do part B and the rest. So now what we have to do is derive an expression for D1. So we already reasoned that D1 is less than D2. We have to derive an expression for that. So in order to do that, we're going to use the fact that the acceleration when it enters a region with friction is mu g to the left. And we know that the velocity when it enters that region is ma v naught over ma plus mb, right? So this is some of the stuff I wrote down before I stopped recording. So in order to figure that out, right, so we got to write an expression for D1. We know that it's accelerating, and we are going to figure out the displacement, and we know what the initial velocity is when it enters the region is this here, the ma v naught over ma plus v mb, and then the final velocity is going to be 0. So I'm going to use the time-independent relation, vf squared equals v naught squared plus 2ax, where x is just d1. All right, so I know vf squared is 0. V naught squared is ma v naught over ma plus mb quantity squared. And then I have here, my acceleration is mu g to the left, so that's going to be negative for this one. So minus 2 times mu g, that's the acceleration. And then the displacement is just d1. So then I'm going to move this to the other side, and I'm going to divide both sides by 2 mu g. All right, so actually I'm going to do both steps at the same time in the interest of time. All right, well, actually, that's fine, whatever. All right, so ma v naught over ma plus mb. Okay, all of that squared. And then at the very end, I'm going to divide both sides by mu g. I'm sorry. It was 2 mu g times d1. All right, so all I did was I moved it to the other side. And then I'm going to divide both sides by 2 mu g. Okay, and then that's my expression for d1, 2 mu g. All right, and that's my expression for d1. Okay, so that's the answer for part B. All right, I basically just used time-independent relation and the fact that the acceleration is going to be mu times g to the left. All right, and then C, indicate whether or not your equation you derived in part B is consistent or inconsistent with the claim you selected in part A, and then justify why the equation and claim are not consistent. So basically, in terms of the consistency with part A versus part B, so for part B, the equation would be D2 is equal to 2ma times v naught over 2, right? So v naught over 2 over 2ma plus mb. And all of that squared divided by 2 mu g. So we talked about this earlier, how the 2ma v naught over 2, right, that just comes out to ma v naught, right? So the numerators are going to be the same, but the denominators are going to be different, right? So that's basically the reasoning. I'm sorry, the denominator, because it's a complex fraction, right? So for my D2, right? This term here, the MA V naught over 2MA plus MB, that's going to be smaller than what it was for D1, right? So this here, this term here, I'll just clarify, this is going to be smaller, okay? And this term here is the same, right? So this matches our reasoning for our selection for answer choice A. We said that D1 is going to be greater than D2 because they're going to have the same deceleration, okay? But the velocity in trial 1 is going to be larger than the velocity in trial 2 as indicated by our equation, right? So I would write the, this is consistent because we clearly see from this equation that D2 is going to have a smaller initial velocity for trial 2. It's going to have a smaller initial velocity when it enters the region with friction. And because it has a smaller initial velocity and it has the same deceleration as in trial 1, we know that D2 has to be smaller than D1, and that matches our reasoning, right? So just writing the equation down for D2 and showing, this is clearly smaller because look, this numerator for this complex fraction has a larger denominator, and if you have a fraction with the same numerator and a larger denominator, well, that whole quantity is going to be smaller. So hopefully that makes sense. But either way, I'm going to post this video. So if you have any questions on this, definitely stop by for Pride or after school, or if you want to review any of the content before we have the exam on Wednesday, just let me know. So